We know that enzymes catalyze chemical reactions by lowering the energy of activation. Let's take a look at how physically an enzyme will act upon the reactants of a reaction to actually do this. So first of all, the reactants that the enzyme acts upon are going to be called substrates. So really, for a chemical reaction that's catalyzed by an enzyme, reactant and substrate is the same thing. What the enzyme will do is it will bind to the substrates, and this forms what is called an enzyme-substrate complex. The place where the substrate will bind the enzyme on the enzyme is called the active site. It's called the active site because this is where the activity takes place. This is where the enzyme can change the reactants into the products at the end of the chemical reaction. Now, when the enzyme grabs a hold of the substrates or the reactants, it kind of hugs them tight and it changes its shape just a little bit to make sure that all of the amino acid R groups in the enzyme that are necessary to help catalyze the reaction are pointed in the right direction towards the substrates. This change in the enzyme's shape is called induced fit. All right, so down here it says induced fit of a substrate brings the chemical groups of the active site on the enzyme into position that will enhance their ability to help catalyze the chemical reaction. So let's take a look at an enzyme, a substrate, the active site, and this induced fit. So in blue here, we've got this big globular enzyme here. And you'll notice this little cavity. This is the active site on this particular enzyme, and it's perfectly going to fit this little substrate in here. You'll notice that when the substrate fits in there, the enzyme kind of clamps down on it. So the full shape doesn't change drastically, but just around this area where the substrate is in the active site, the enzyme will kind of clamp down on it, and that change in its structure will allow the R groups of the amino acids here that line the active site to point towards the substrate so they can help catalyze the chemical reaction. And so this entire structure here is called the enzyme-substrate complex. Now, once the enzyme grabs a hold of the substrate, how does it actually lower that energy of activation? There are multiple things that the enzyme can do to accomplish this. We're going to take a look at 4 options on this slide. So option number 1, an enzyme can lower the energy of activation barrier by orienting the substrates correctly. Let's think about this for a second. So our example that we've been using in this chapter, right, we were looking at molecules A, B, and C, D. We wanted to break those bonds between A and B, and the bond between C and D, and we want to reform bonds A and C and B and D. So imagine first the reactants here, right? These reactants, imagine you have a lot of AB and a lot of CD floating around together in a solution, right? And when they're floating around in there, they have that thermal energy and they're bumping into each other, right? The percent chance that you have AB and CD bumping into each other in exactly this orientation is going to be pretty slim, right? These molecules are moving in every which direction, so they might bump into each other AB and CD this way, right? That's not going to help you form these molecules over here. You might have AB bump into maybe CD this way, right? That's also not going to help to make those molecules. So the percent chance of A, B, and C, D bumping into each other the right way to make these guys is slim when you just have molecules moving around randomly in a solution. So what the enzyme can do is it can take A, B, and C, D and only allow them to fit into the active site in one position, in one orientation, and that will help to ensure that 100% of the time A, B, and C, D interact with each other in the right way to get the chemical reaction to proceed. I'm going to come back to 2 and 3 on this slide in a second, but let me just show you what orienting substrates correctly might look like in a cartoon version. So here we've got our substrates, red, and green, and in purple we have the enzyme. You'll notice that the enzyme's active site is a very special shape, and the shape will only fit red and green in one orientation. And this one orientation is the perfect orientation to allow the enzyme to convert red and green into blue and yellow. At the end of the chemical reaction, the enzyme will release the products and it will return back into its original shape, keeping that active site now open to accept more substrates if they are available. All right, back to this slide. So that was one option, right? To lower the energy of activation, the enzyme might orient the substrates correctly. Okay, number two. This is another way in which a cell's enzyme can lower the energy of activation. Let's say I had a plastic ruler, right? This is not a ruler, but use your imagination. If I were to take that plastic ruler and I were to hug it real tight and I start to bend it, what do I risk doing to my ruler? Hopefully you said, well, you're going to break it, right? And so this is kind of what the enzyme can do. It can take those substrates and it can hug them real tight, and it can put a strain on the bonds that are existing in those reactant molecules, making them a little bit easier to break, so you can break those bonds and reform new ones to make the products. So straining the substrate bonds is our second option for how enzymes can reduce that energy of activation. Number three, my favorite one. In this case, the enzyme might provide a favorable microenvironment for the chemical reaction to take place. So let's say this chemical reaction that this enzyme needs to catalyze needs to take place in a slightly acidic environment. The trouble is, though, that the inside of the cell is usually just around neutral. And so the reaction is not going to take place very quickly inside the cell in that neutral environment. So what the enzyme can do, I'm going to take a couple steps back here. What the enzyme can do is when it takes that substrate into its active site and it forms that induced fit, what that will probably do is it'll turn the R groups of the amino acids that line the active site out towards the substrate. And what if all of those amino acids here that line the active site have R groups that are acidic? What that will do is it'll create a tiny little microenvironment in here that is acidic, allowing for that chemical reaction, changing the substrate to the products to happen a little bit more easily, even though the outside pH here on the outside of the enzyme is neutral. You get that tiny pocket of acidic solution on the inside of that enzyme. All right, and then number four, this one. So it says an enzyme might covalently bond to the substrate itself. When you make a covalent bond, you're actually changing the structure of a molecule or molecules. And so originally, this kind of contradicts what we said about enzymes. We talked about how they are not changed in any way. They're not consumed by the reaction. This might seem kind of counterintuitive, but the enzyme can actually make a covalent bond with its substrate. And when it does this, it's a temporary covalent bond that initiates the catalysis of the chemical reaction. And once the enzyme converts reactants into products, then that covalent bond is broken, returning the enzyme to its original shape, leaving it essentially at the end of the chemical reaction untouched and unchanged, even though somewhere in the middle there, that covalent bond was formed between substrate and enzyme to get the reaction going.